Good morning, my name is Hao Dongduan, and today I'm glad to present our work, Mitigating Representation Bias in Action Recognition. In this work, we propose a new algorithm for devising action recognition, as well as new evaluation protocols to directly evaluate the biasing effect. We always find deep action recognizers highly biased towards static clues. They have a strong tendency to recognize actions based on the scene of objects. That behavior is unwanted and restricts the generalization capability. For example, slow-fast trained on kinetics tend to recognize actions based on scenes and make mistakes on playing piano or shooting goal with novel scenes. Before working on debiasing action recognition, a good question is how to quantitatively evaluate the debiasing effect. In action recognition, the previous work applies the debiasing algorithm to supervise pre-training, fine-tune the pre-trained weight on downstream tasks, and use the downstream performance as metrics. Such evaluation is indirect since there is no obvious correlation between debiasing effect and downstream performance. Instead, we designed two protocols to directly evaluate the debiasing effect. The first protocol is to redistribute the dataset to manually create Train-Val splits with significant domain shift. For example, for scene debiasing evaluation, we can first obtain the pseudo-scene labels for Kinetics videos with pre-trained scene classifiers, and then redistribute videos in each class based on the frequency of pseudo-scenes to form the new Train-Val splits. Thus, the Train-Val splits will have great scene distribution shift. When training and testing on the new data splits, we can observe huge performance drop, and we expect the debiasing algorithm to mitigate that gap. The second protocol shares similar ideas. The only difference is, in this protocol, we use out-of-distribution videos with large scene distribution shift. To create such an OOD test set, we begin with action labels in Kinetics and consider some rare scenes, and use the combinations as queries to obtain web videos from YouTube. We test action recognizers on the collected OOD test set and also observe a similar huge drop. We then present our debiasing algorithm. It includes two major components, namely spatial-aware multi-aspect debiasing and OmniDebias. In SMAD, we use multi-aspect debiasing. For each single bias factor, we add an adversarial loss term, which is jointly trained with the cross-entropy loss for action recognition. In the backbone, we also add a spatial-aware actionness relating module. The module predicts an actionness score for each single pixel and reweights the feature map with predicted scores. The SAAR module helps the model to focus on the action performers and suppress irrelevant backgrounds. SMAD outperforms other debiasing or domain adaptation algorithms, while it requires no access to the validation data distribution. We also propose OmniDebias to leverage web media for bias mitigation via joint training, considering their richness and diversity. We first try to jointly train Kinetics and other web datasets with the OmniSource framework and find it a strong baseline with great debiasing effect. We further propose a data selection strategy to deal with the imbalance problem. In web datasets, the distribution over the bias factor can be even more imbalanced than kinetics. Based on the same approach for split redistribution, we propose a simple yet effective heuristic solution. We divide the web dataset into three equal-sized parts and only choose videos with least frequent debiasing factors for joint training. Joint training with that unbiased split, which includes only one-third data amount, can significantly outperform joint training with all web data on every debiasing benchmark. We did extensive experiments to evaluate the debiasing effect of SMAD and OmniDebias. On all benchmarks, they significantly improved the accuracy on validation sets with large scene distribution shift. Moreover, the improvement of two components are complementary and can be combined together. Here we show some qualitative examples. When visualizing the CAM and actionness score of models trained with our algorithm, we find that our model can focus on the action performer and suppress irrelevant backgrounds. That's all of my presentation, and thanks for your attention.